For driving, but for the written test, you don't have to. Yeah. Yeah. Back in my day, you just had to show up, sit there for a long time, and hope you didn't get the meanest woman.
Oh my God.
They were all mean, though.
The girl that works there now, she's really mean. Like, when I was there, she was
I have not been to the DMV in Elkin in several years because I have not had to renew my license. But the times I have went, it's been mostly men working, and they were really, really nice. But you can't mess it up. Mm-hmm. Really? Won't even let you know.
Oh my God, they didn't let me.
Just sit there, click. Yeah. Yeah. All right. Okay. All right. Okay. Okay. Homework is going to be inevitable if we don't get through this. Okay? All right. Okay. All right. Jamie throws a rock from a tall bridge. He counts and it takes the object 3 seconds to hit the ground. How tall is the bridge? Okay? So this time we don't, again, like number 3, we don't know how tall the bridge is. I'm going to use a fancy variable here. I'm going to say that h of t, we used that yesterday, that's not the fancy variable, equals h sub 0 minus 16t squared. Okay, now that is a fancy variable. They use this a lot in science sort of context. H stands for height, and putting that little subscript on it that says 0 means it's the initial height, the height whenever the time has not started yet, when time is 0. So it's just like having another variable like h, or when I did the one yesterday, we used the question mark, right, because we weren't sure what it is. This is a hit the ground problem. What's the height when you hit the ground? So whenever anything hits the ground, what's its height? 0, right? So height, not initial height, but height goes right here. So we're going to put a 0 right here. We don't know h sub 0. That's our initial height. We don't know what it is. We do know the time it took to hit the ground, which is 3. So if we grab the calculator, and if you don't have yours, you don't have to get up to get it. You can use Desmos, because we'll need Desmos here in a minute. Good gracious, I got all this stuff open. Yes. It means something. It's either an x-intercept or a y-intercept or a vertex for that. Okay. All right, so if we do 16 times 3 squared, we're going to get 144. So 0 equals h minus 144. If we just, h sub 0. If we just move that over to the other side, h sub 0 is 144 feet. So that bridge would be 144 feet tall. What? These are very applicable to physics. Maybe a little. All right. Well, I think that some of you maybe think that about all word problems, period. So. Uh-huh. I'll make the ones you put in blank. I'll make you another problem similar to it. I can't give you the same. I can't do it today, but I'll give it to you tomorrow. What did Monday? Combined on Monday. All right. So example 5: a penny is dropped from a building that is 324 feet tall. How long will it take for the penny to hit the ground? So, one thing really important for this is like to know what the question is asking for. To know like what variable you are going to find. What if my answer is how long? What kind of answer am I going to have here? I'm finding time, right? So be real careful to make sure you're answering the right question, because sometimes I'll ask how long will it take to hit the ground, and somebody will answer 65 feet. That would be like if I asked you, how long does it take to get to Walmart, and you told me 7 miles. Right? I'd be like, what is wrong that you answered me that way, right? It wouldn't make sense. So make sure you read the question really carefully, because sometimes students give answers that don't make sense because they've put things in the wrong place. So it's asking for how long, so that's T that we're trying to find. The building is 42 feet tall, so that's going to be 342 is where we're starting from, and then we subtract our 16t squared, that's for our gravity. And this is a hit the ground problem. Whenever something hits the ground, its height is 0, right? So we put in a 0 for the height, which is our h of t. So we got 342 minus 16t squared. All right, Haley, tell me how to solve that equation if I want to get that t by itself. Good? Not the 16. It's closest. We got to deal with that 342 first. So we're going to subtract that 342. So we got negative 342 equals negative 16t squared. What would we do after that? Very good. And we're going to grab our calculator for that. Negative 342 divided by negative 16. It's going to be 21.375. And then what's the last thing we're going to do, Haley? We will square root here. And if we square root that number, we'll get 4.623. And this is time. So how do we measure time? Seconds. Okay, all of these problems are for things that were dropped, right? So we need to think about now what's going to happen if we throw something into the air, or we could throw it down as well. So first thing we're going to do is we're going to imagine that we are somehow in an environment that has no gravity. Okay, so we're basically outer space. We have to be in outer space for this to be the case. So a pumpkin is launched from a height of 20 feet at a speed of 40 feet per second. Okay, so wherever we're at in space, we are going to launch this pumpkin from a height of 20 feet. So at time 0, what's the height of the pumpkin going to be? It's going to be 20. So our height would be 20. All right, after 1 second goes by, how high would our pumpkin be? Okay, how do you know it's 60, Evan?
Because there's no gravity, so there's nothing to stop the pumpkin. It starts at 20, and it goes 40.
Okay, it goes 40 feet per second, so 40 feet every second, right? So it started at 20. In the first second, it's going to go 40 feet. Okay, where would it be at 2 seconds? 100. Then 140, and then 180. Okay, and it would continue to do that, right? Obviously, if we throw the pumpkin on Earth, it would start at 20, and it would go up, 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 but it'd kind of slow down as it was going up, right? And then eventually it'd stop, and it'd turn around and fall back to Earth because gravity would have overtaken the force that we've had going on the pumpkin initially. But if we are in space, if there is no gravity, that pumpkin is just going to keep on going up forever and ever and ever and ever and ever, right? We'll never see that pumpkin again. Let's also consider that if we are floating in space, we have just sent ourselves going the opposite direction at that same speed, which might be an issue. So this pumpkin is just going to keep going up, up, up. We need to write an equation for this pumpkin. Okay, so it's going to be h of t again. And we need to write an equation that will give us these numbers if we start plugging in time. So, any guesses there?
H plus 40t.
You got h plus 40t. Okay. I think we've got some good stuff happening there. But h right here, what is h? Okay? So we could call it like you're talking like h sub 0, the initial height, right? For this particular case, it would be 20. So we'd want to plug in 20 right there so that we have an equation that only has one variable. So if we want to know after 20 seconds, we could just plug in 20. 20 plus 40 would equal, 40 times 20 would give us how high the pumpkin would be. This will work fine if we start plugging in numbers. If we plug in 1, 20 plus 40 times 1 is 60. 20 plus 40 times 2 is 100. So this gives us these numbers. Okay? All right. C asks us to think sort of along the same lines, but suppose another pumpkin is launched from a height of 15 feet at a speed of 25 feet per second. We want to write an equation for this pumpkin here, also still no gravity. Okay, thank you. So what would this equation look like? What do you think, Kaylee? Perfect. Okay, so it would be, you would always have your starting amount where you start from, and then it's just going to be plus whatever speed you're going times the time, right? That'll tell you how far it would go. Okay. These equations would only work if you had no gravity, because these pumpkins would just keep going up, 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 up forever. So, now, let's put it all together, okay? All right, same scenario, pumpkins launched from 20 feet, initial upward velocity of 40 feet per second, but now we're on Earth, gravity is a factor. Write an equation that would give the height of the pumpkin after t seconds. So, we're going to have h of t. What do you guys think? Okay, we got to start with 20. That's where we're starting from. Please wipe that up. Y'all gonna have me outlawing drinks. I don't want to, but possibly. Okay, put the lid back on. Alright. Okay. Alright, so we have 20. And the initial upward velocity of the pumpkin is 40, which means we're throwing it up just like we threw the pumpkin in space. It's got a speed of 40 feet per second whenever it starts out. So let's imagine we're in space. What's our equation look like if we're in space? Okay? But we're not in space. So we had something we used for gravity. What was it? minus 16t squared. All right, so let's use this equation to fill in the table below, okay? So if I plug in 0 to this, I'll just get 20, right? If I plug in 0.5, let's see what we get. 20 plus 40 times 0.5 minus 16 times 0.5 squared. Get 36. Pumpkin's still going up, right? If we plug in 1, we'll have 20 plus 40 minus 16. So 60 minus 16 is 44, I think. It is? Good. Then 20 plus 40 times 1.5 minus 16 times 1.5 squared gives us 44. Again. Yeah. I think we're probably going back down.
Are we in space or are we not in space?
We're not in space. We're on Earth. Yeah.
Since it stays the same thing.
Right. Then we've got 2. We're going to plug in 2. All right, we get 36. All right, I bet I know what we're going to get for 2.5. I typed something in wrong there, didn't I? No.
I believe it's
2. I put 2 instead of 40. Yeah. There we go. Let's try that. 20. Maybe, but maybe not. It could go to negative, which we would know we would need to quit using this equation at that point, right? Yeah, negative 4. Okay. Okay, it asks us now to graph these on Desmos. So, let me pull that up. They're Quiz Bowl t-shirts. So if we put in these points, I got 0, 1, 0.5. 1.5, 2, 2.5, 3. And then I've got 20, 36, 44, 44, 36, 20, negative 4. And I can't see it right now. Did I show you guys this plus sign right here? Somebody showed me. I couldn't remember if it was you or the other class. If you click this little plus sign right here, it will just give you perfect view. It might have been y'all. I was thinking it was Pre-Cal that showed me, but I might be wrong. It was you. Thank you. All right. So we have our graph here. Here's my question to you. Do I have more questions written right here? Okay. All right. So here's my question to you. How high does that pumpkin go? Just look at the table right now. That's the highest I see on my table. So do we think that this pumpkin goes up, hangs out right here for a half a second, and then comes back down? Right. So if you throw something into the air, oh yeah, that'll work great. Who is it now? Hello? Yes. Okay. All right, thanks. Bye. You're supposed to stop by the office when the bell rings. So hopefully whatever you need. Hopefully. All right, so if we throw throw something into the air, straight up into the air, did it stop and hang out for half a second up there at the top? No. But did it stop? It changed from going up to going down, so it had to stop. But it's, yeah, that is different, but it had to stop going up so it could start coming down. It had to change direction, right? So there's like a momentary stop right there. And as it goes up, notice like here it went, like each one of these little bars right here is a half a second. So the first half a second, it goes up quite a bit. Then not quite as much. Then I imagine it went a little bit higher than 44, right?
44.
So like 44 and a half or 45 maybe. And then it comes back down, right? It slows down as it's going up. And then it stops momentarily for a not measurable amount of time, right? It stops and turns around. And then it speeds up as it comes back down. So if we take our equation and type it in, so instead of just graphing our points, if we take our equation, we can see it did go a little bit higher, and it was 45. So it went 1 foot higher than 44. It did go up to 45 feet there. We can also tell when exactly it would hit the ground from this. So right here is where you would hit the ground. It'd be 2.927 seconds. So like on our table, we've got at 3, you're at -4. We're going to quit using the equation once it starts to hit the ground, right? Because it doesn't apply anymore. It's not actually going, unless it's going into a hole where it can continue to fall, then we wouldn't want to use this anymore when it hits the ground. Yeah, we're not going to do that right now. All right, so the general equation for the height of a projectile after t seconds is going to be this. H of t equals h sub 0 plus v sub 0 t minus 16 t squared. All right, so we've got some of those weird variables right there. We are going to make sure we label everything so we know what we're talking about. First of all, H is going to be height, and T is time. Height in feet, and time is in seconds. Remember, if we're going to use meters and feet, or if we're going to use miles per hour, we would have to have a different equation. This only applies to feet and seconds on Earth. So this only applies on planet Earth. And what did we say this ignores? Air resistance. So if we are dropping a feather, we would not want to use this equation because it's not going to behave in this manner, right? But if it's something fairly dense, something like a pumpkin or a ball, bowling ball, something like that, a pin, something that doesn't have a lot of air resistance, you'll be pretty close, right? Specifically, I do want to say this H sub 0 is going to be your initial height. And V sub 0 is your initial, pretty close, initial upward velocity. So whenever we talk about doing this, it is easiest to picture if you're just like shooting something straight up into the air. Because then all of its velocity is upward, right? if we shoot something at an angle, which we're more likely to do, like whenever we do our catapults, we don't want to shoot our pumpkin straight up into the air because our goal is to have the furthest distance. So you're going to, ideally you shoot it at a 45-degree angle. That's going to get you the highest, the longest possible range there. So if you shoot your pumpkin at a 45-degree angle, some of its velocity is going upward and some of it is going, forward in that case. So initial upward velocity we're going to find later is difficult to measure, but it's possible for us to find it using other things. Okay. All right. So questions. That's our formula.
When I was typing in the equation, what you found decimals, it's like like you can't.
Let me look at it real quick. Go back over here to this part right here. You got to have. It said H of T instead of. It's not just a parentheses. It's not showing the whole thing. So you'll have to have.
Oh, I got it.
Yeah. That was what's wrong. Okay. All right. So let's look at how to use this. So I've kind of broken this up into sections. Not right. Learning things. Let me look real quick though. I need to see which one of these I need to do first because I can't remember which one of these comes first. All right, and you do need to have Desmos pulled up. Okay. All right, I know which one we need to do first. All right. Okay. We're going to do our maximum height first. Okay, so Desmos is going to, once we learn how to use this equation, Desmos is going to make this pretty simple because we don't have to do a lot of calculations. We just have to know where to look on our graph for our answers. All right. All right. Okay, I am going to split screen this. You can pull up Desmos. We're going to need it. I'm going to clear out what we had already.
Oh yeah, I just found out that so we have to like make our designer letter for the catapult.
Yes, tomorrow.
Is due tomorrow.
Yes, not the catapult, just your design. So I just need, if it is already made, you can send me a picture of it. So you got a few options. If you have already made it, you can send me a picture of it. Then that'll be good. You don't have to design something that's already been made. If you are specifically going to follow the directions of a website, but it needs to be like, I actually looked at this, I actually read it, and this is what I want to do, and I have the stuff to do it and can do it, you can just send me a link to that website. Or if you are coming up with your own design, I need you to draw out a picture of it and give me a list of the materials that you're going to need for that. So thank you for reminding me about that. It is due tomorrow, so make sure your plan is here tomorrow because that will be part of your grade.
So for the part of design, do we have to like measure like how long each thing is?
It would probably be a good idea for you to plan ahead for that. But if you are doing something like a spoon taped to a binder clip sort of thing, you don't have to like get those and measure them for me. If you're going to like actually build it, it would probably be a good idea to at least have rough measurements of how you're going to cut the wood and everything for that. So that is due tomorrow. Make sure you've got that for me. All right, so let's see. The design is due tomorrow. Yeah. Yeah, not the catapult itself, but the design. All right, so a lot of these problems are going to start the same way. H of t equals h sub 0 plus v sub 0 t minus 16t squared. That's the equation we just did, right? It gives the height of feet. H sub 0 is the initial height. V sub 0 is upward velocity. So all of this stuff at the beginning we're going to see on a lot of these questions. It's just telling you about the equation, right? We've already kind of went through where that equation comes from, so hopefully you understand it well. So a pumpkin is launched into the air from an initial height of 7 feet at an initial upward velocity of 85 feet per second. What is the maximum height that the pumpkin will reach? Okay, so what you've got to do for these problems is find where you need to plug these numbers in. So 7 and 85, you need to see where you need to put those in. And then you're going to look for, in this particular case, maximum height. Okay? So we'll start with our equation. Where should my 7 go? Okay? Initial height is h sub 0, so I'm going to put a 7 right here for my h sub 0. What is the 85? V sub 0. Goes right here. So it'll look like this. H of t is going to equal 7 plus 85. You still have a t in your equation right there. Minus 16 t squared. You're not replacing the t's. So if I go over here and type that in, I will have this graph. Hello? Yes. Thanks. Bye. Kayla, you're leaving your, the projectile motion number 1 is going to be your homework. No, we're going to finish this, but there's a Canvas quiz that's going to be the homework. Okay. It's not a quiz grade, but it's just set up as like a quiz in Canvas. All right. Something looks weird about this. Maybe it's just my... Oh, what did I type in wrong? 85 needs a T. There we go. Now it looks right. So, what's this question asking for? Maximum. Where's that going to be on this graph? Highest point right here. So you're just going to click. There it is. But at that maximum point, my maximum point is going to be 2.656. See, 2.656 is my x coordinate, and 119.891 is my y coordinate. Now, if I ask you a question, what is the maximum height of the pumpkin? And you answer me with 2 answers, I'm going to think that that doesn't make any sense, right? So those 2 numbers right there, both of them are not the answers. Which one is the answer? Okay? It's going to be our y, because our x-axis, when we're doing these problems, the t is on our x-axis. This is time, seconds. The h of t, the height, that is our y-axis. So for these problems, time is your x-coordinate, and height is your y-coordinate. So we're asked for the height, the maximum height that it reached, so that's 119.891 feet for that. Okay, we all right here? Does this make sense? All right. Okay, this one gives us the equation. It gives the height of a ball in feet, t seconds after it is, that should say thrown, not the one, out of a second story window. What is the maximum height in feet that the ball reaches? Okay, we don't even have to think about the equation for this one. It's given to us, right? We're just going to go over here and type it in. Okay? We're going to go over here and look at our maximum point. Is it going to be my x coordinate or y coordinate for this problem?
Wait, where'd you get 84?
Or it's just in the problem.
Oh, I'm on example 3.
Okay? So, Aiden, is it going to be my x coordinate or my y coordinate for this one? It's going to be the y. So, because it's asking for height, which is the y coordinate on these problems. So, 131.25 feet. Everybody okay here? Okay, what was the initial height of that pumpkin? 21. What was the initial upward velocity of that pumpkin? 84, right? So you may get asked some of those questions. You're just pulling them from the equation, if that's the case. Question?
I was like trying to write this down.
That's fine.
I didn't know.
When you type this in over here, you're going to just go to that maximum point, and it's going to be the y coordinate. That's going to be your height. Okay? All right. Okay, example 3. All right, a soccer ball is kicked from the ground with an initial upward velocity of 27 feet per second. What is the maximum height that the ball reaches? This one's a little different than the last one. Well, definitely a lot. It doesn't give you the equation. A little different than the first one as well. All right, 27. Where's that number need to go? It goes for V because it's our initial upward velocity. So 27 goes right here. All right, that's the only number in this problem. And so, like, I can't type this into y equals, or into my Desmos with that h sub 0 right there. Like, even if I can figure out how to type it in with that h sub 0, it's not going to work. I need to put a number here. I must put a number here. I cannot leave this as h sub 0. I have to have something to put there. What number should I use? Okay, why would we use 1? What do you think, Evan?
0.
Okay, why?
Because it's on the ground. 0.
It is kicked from the ground. So since it's on the ground whenever it is kicked, 0 is going to get right here. So sometimes these won't give you an initial height, but they'll give you clues about where the ball is at whenever it is kicked. So it is from the ground. That tells us h sub 0 is 0 in this case, right? Because if something is on the ground, its height is 0. So if we type this in, it's 27t minus 16t squared. So this is not going to be nearly as high as the others we were looking at. It asks for the maximum height that the ball reaches, 11.391. Not very high. So I would say that if you kick a ball into the air, you're probably kicking it at a rate higher than 27 feet per second. If you're kicking it really high. If you're a bad kicker, maybe not. All right, questions? All right, let's do a couple more. All right, this one gives us an equation, and it asks us to find each of these values. So we got h of t equals 15 plus 35t minus 16t squared. I'm going to go ahead and type that in. Let's see with it. If you guys see what I'm doing wrong right there. I've done it twice now, and students do this a lot too. When I type this in, see how my maximum was right there, like on the y-axis, that should not look right to you because that would not happen unless it's just like a drop-in problem. I don't have a T I forgot to type the T in there with that middle number. So if that happens to you, then that might be what you did wrong as well. There, so make sure you're typing it in right. All right, okay. Initial height of the pumpkin. What would it be? It's 15. How can we tell? There's no T with it. If we're just looking at the equation, that is our initial height. The other way you can tell is from the graph. Right here, it's your y-intercept, right? It's where you would start, which also we know this is the y-intercept of that equation, right? So, so you could use the graph or the equation to find that it would be 15 feet. Okay? All right. Let's see, Rosalind, what would our initial upward velocity be for this pumpkin? It's 35. And 35, it's going to be feet per second. We measure velocity in distance divided by time, so feet per second for these particular problems. And Blakeland, if I want to find the maximum height of this pumpkin, what am I going to do? Okay, so we're going to use a graph for this. So if I go over here to the graph, where would the maximum be on that graph? On our Desmos graph here. We've got this upside down parabola right here. It's going to be at that highest point. Okay, so we've got 1.094 and then 34.141. Ian, which one of those is my maximum height? The Y. So we're going to have 34.141 feet. And I keep using pumpkin over and over again because we're going to do the pumpkin chunking experiment, but it could be something besides the pumpkin for that. So right now what you are going to do is you're going to go to Canvas. On Canvas, there is an assignment. Let's see, we didn't get to this today, so it's going to get moved tomorrow, which is fine. Move this one to tomorrow. Okay. You are going to do this assignment right here, which is projectile motion number 1. It is going to have 7 questions. It's like a Canvas quiz. It should let you take it more than once. Yeah, and I think it lets you see your responses, but I don't think it gives you the right answer. So if you miss it, you'll have to rework that problem. But it does not pull from question banks, I don't believe. So it should give you the same questions again, so you'll know you're fixing those ones that you missed. Yes, you may use Desmos. It is not embedded on this because this is just an assignment. Even though Canvas calls everything a quiz that like has answers to it. It's just an assignment, so you can have a second tab open for Desmos and go back and forth. That's fine. Yes. Next Thursday is going to be our test. We are going, let me look at my schedule. We will have, so we did that quiz already. We will have, no, we don't have any more quizzes for this unit. We won't do a quiz on the projectile motion stuff. We will have, we will review Tuesday and Wednesday next week. Thursday we'll have a test. Okay. Also Thursday's when your catapult's going to be due for me. I want them all here on Thursday because when we come back from Easter that Tuesday, we're going to do the catapult project. So I want them all here that day because I'm afraid if I make them do on that Tuesday that you guys won't have it. Thank you. Yes. All right. So I need to give those of you who are not going to be here tomorrow your Oh, come on.